So if I have a regression equation that looks like this, the mean of y given, and then say two predictors there. If I have an intercept plus a term, it's called a main effect for x, plus a term, it's called a main effect for w, plus this third term with its own coefficient times the product of x and w, this term right here is called the interaction. First, let's write down the definition of an interaction in a couple different ways. So the idea with an interaction is that the relationship between x and the mean of y might depend on w. Okay, when we write down an equation to describe the relationship between x and the mean of y, maybe that relationship is actually different depending on what w is. I can say it another way. An interaction occurs when the effect of one predictor on the outcome variable depends on another predictor. Now, I don't love this word effect. It's a very common word in regression. The problem is it's a causal word. It implies we have causation when that's not what we're talking about. We're just talking about drawing lines to connect the mean of y to x for any set of predictors, even if they're not causally related. But I'm putting that in here because you may have heard interactions discussed that way before. So if this is what an interaction is, then when you hear people say there's no interaction, right, that occurs when the effect, and again, there's that word that I don't love, but it's common in regression, so I'm trying to write this in a way that might ring a bell and make you realize you've seen this before, maybe. If you've had ANOVA or multiple regression before, you may have seen this. When the effect of one predictor on the outcome is independent, does not depend on, independent of the other predictor. So if I try to say this just in words, just in a lay way, suppose I'm looking at the relationship between high school GPA and college GPA, right? It could be the case that if you are a science major, then there's a strong relationship between your high school GPA and your college GPA. Maybe it's possible that your grades in high school are very good predictors of your grades in college if you're a science major. But I'm completely making this up. Suppose it's the case that your high school grades are not good predictors of your college grades if you're a social science major. Why? Well, there's not as much social science kind of taught in high school, right? You don't spend as much time taking, maybe economics, maybe I'm making this up, right? Again, if the relationship between your high school GPA and your college GPA differs depending on what your major is, that's an interaction. So conceptually, this is what it is. But I want to focus on this equation, right, and what it implies about what's allowed to happen in the data set. So let's draw it in blue to match that equation. Okay. So here's x and here's y, and I'm assuming here that x is continuous and y is binary, but actually that doesn't have to be true. I think that's a helpful way to illustrate what's going on here. If you do not have an interaction, okay, if I do this with no interaction allowed, then my equation, my linear regression equation, is the mean of y given x and w is equal to some number plus some number times x plus some number times w. And again, I left off the interaction. Well, what that implies is that when w is equal to 0, the mean of y given x is equal to what? Well, beta 0 plus beta 1x, and the w term's not there. And it also implies that when w is equal to 1, the mean of y given x is equal to beta 0 plus beta 1x plus beta 2 times 1. In other words, my intercept has changed by some amount beta 2. Okay, so we've looked at this before. This is not the first time you've seen this in this lecture, but the idea is that if I leave off the interaction, then there's some line that relates x to the mean of y for w equal to 0, and there's some other line that relates x to the mean of y for w equal to 1, but those lines have to have the same slope, right? Because in both these equations, I have beta 1 as my coefficient for x. What is allowed to be different is the intercept. So this is when w is equal to 0. So the idea here is that, like, if this is 0, then this amount here is beta 0, and this amount here is beta 2. It's the amount by which the intercepts differ from each other, but the slope of both of these lines is beta 1. If there's no interaction, that's what's going on. However, if I write the equation so that an interaction is allowed, so that it's possible, the mean of y given x and w is beta 0 plus beta 1x plus beta 2 w plus beta 3 x times w, then when w is equal to 0, what I've got is that the mean of y given x is equal to beta 0 plus beta 1x plus 0 plus 0. So that's fine. I can draw this, right? Here is the beta 0. This has slope beta 1. I can label this. This is the equation when w is equal to 0. And then when w is equal to 1, I've got the mean of y given x, and it's equal to beta 0 plus beta 1x plus beta 2 times 1 plus beta 3 times x times 1. And again, we've done this before, but I want you to see it here too. If I've got beta 0, I'm going to group all the terms that don't have x's in them, and then I'm going to group all the terms that do have x's in them. So here's the new intercept of my line, and here's the new slope of my line. Because of this interaction term, the equation allows not only for the intercept to be different in these two lines, but also the slope. So now, sure, the intercepts might differ by beta 2, but now also the slope of this line is equal to beta 1 plus some number beta 3, which could be any number, right? The slopes have now been allowed to differ as well. So I think it's important for us to point out that the no interaction model is a special case of the model with an interaction. If you write down this model with an interaction and then just say beta 3 is equal to 0, now you've got the case with no interaction, right? That would just mean that last term isn't there. So I can say that the no interaction model is a special case of the model that includes an interaction, where the coefficient of the interaction is equal to 0. So again, I'm emphasizing that we have that the no interaction model is a special case of the interaction model, because this is the opposite of the order in which this is often taught, especially in the intro class. So usually you'd start with saying, hey, let's just put in our predictors into the model. That's the simplest model. And then if you want to learn about something more complicated, hey, we could add this interaction term. Let's discuss what that is. But that's not actually how data works, right? Really, there's no reason that in the world usually the relationship between x and y would be the same for all possible values of w. Why should it be the case that the relationship between high school GPA and college GPA is the same for every major? Some majors involve courses that appear more in high school than others, right? So the more general case, the case that the model that's more likely to be appropriate for more data sets is the one that allows an interaction, the model that allows the relationship between x and the mean of y to differ for different values of w. And then we might discover that we just happen to have a data set where these two lines are parallel. Great, that's a special case. But we should always be looking at the most flexible model possible, because in the real world, data rarely even follows straight lines like we're describing here, let alone parallel straight lines. Before I stop here, the other thing I want to say is just that I've discussed this concept for an example where X is continuous and W is binary, but that doesn't have to be the case. For example, suppose I write down, I'm just going to the same equation again. The mean of Y given W and X is beta 0 plus beta 1. I think I reversed the order this time. Let's not do that, let's do this. Beta 1x plus beta 2 w plus beta 3x w, okay? Suppose these are both binary, right? If they're both binary variables, if they're both binary predictors, what that means is this equation now implies a mean of y for each different combination. So I won't write all of them here, but this implies that the mean of y, oops, didn't mean to turn that yellow. It implies that the mean of y when w is equal to 0 and x is equal to 0 is, well, if I plug in zeros for all the x's and w's, it implies that beta naught is that number. It also implies that the mean of y when w is equal to 0 and x is equal to 1 is, well, let's plug it in, beta 0 plus, well, we do have the beta 1, but we don't have the beta 2 or beta 3. I changed my mind. I am going to do all of them. If we have the mean of y given w is equal to 1 and x is equal to 0, well, I've got beta 0 plus, I don't have the beta 1 because x is equal to 0. I do have the beta 2, but I don't have the interaction because x is equal to 0. And then I could also have the mean of y given w is equal to 1 and x is equal to 1. And now all of these coefficients are going to end up in here. Okay, so I could, again, have this model. It works perfectly fine with binary predictors. How do you interpret these? Well, if this is my model, then beta 0 is the mean of y when both predictors are 0. Beta 1 is the amount that my predicted mean of y changes when w is equal to 0, but x goes from 0 to 1. Beta 2 is the amount that my prediction of y changes when x is equal to 0, but w goes from 0 to 1, right? And then this beta 3 is kind of hard to interpret, right? But it's the number that you put in there to make sure that the mean of y can be any number for this fourth combination. If I excluded this term, here, if I insisted that beta 3 has to be equal 0, then when w equals 1 and x equals 1, right? Then my prediction of y has to be equal to the mean predicted when both values are 0, plus the effect that I saw for x when w is equal to 0, plus the effect I saw from w when x was equal to 0. But it has to be exactly the sum of those two. And when you put in a beta 3, it can be any old number. Let me draw you a picture to show you what I mean by that. So let's see. Let's suppose that I have some data. I'm just going to make some data. Maybe it goes like this. So this is the case where w is equal to 0 and x is equal to 0. This thing is y. Y is on this axis. And this is where w is equal to 0 and x is equal to 1, and where w is equal to 1 and x is equal to 0, and the case where they're both equal to 1. Okay, so here, if I were to use this data set to try to estimate these values, well, okay, here is beta 0, right? And put a hat on it. You'll start to see that notation. You put a hat on the parameter when you're estimating its value. All right, and beta 1 is the amount that my predicted mean changes when we go from x equals 0 to x equals 1, when w is equal 0. All right, and beta 2, well, see, here's what I want my prediction to be when w is equal to 1 and x is equal to 0. So beta 2 is the amount by which, the amount that I add to beta 0 when I have w equals 1, but still x equals 0. So here's the thing. What I want, given this data set, is for the mean of y to be less than the initial beta 0, right? this is going to be when W is equal to 1 and X is equal to 1. So this needs to be the mean when they're both equal to 1. But if I don't have an interaction term in here, then I'm going to insist that this number right here be equal to beta 0 plus beta hat 1, beta hat 0 plus beta hat 1 plus beta hat 2. If I don't allow a beta hat 3, I'm going to get a crazy number here. This isn't going to work at all, right? If you look at what beta 0 is and what beta 1 is, what beta 2 is, if I add all those three things together, I get some number way, way up high, when actually the combination of W equals to 1 and X equal to 1 gives you a mean that's lower than any of the others. So I need this additional value, which is going to be some really negative number here to counteract the other three. So the point of all this is you need the interaction, or else you are really restricting what the relationship between the different predicted means can be. You're insisting that the amount, if you don't put the interaction in, you're insisting that the effect of X going from 0 to 1 is the same when W is equal to 0 as the effect of going X equal to 0 to X equal to 1 when W is equal to 1. Whereas in this picture I drew here, when X goes from 0 to 1 and W is equal to 0, we have a positive effect. But when X goes from 0 to 1 and W is equal to 1, we actually have a negative effect. So I know I've scribbled all over this picture now. The point is, if you leave off the interaction, then you are making the very, very strong assumption that the impact of one variable is the same regardless of the value of the other variable. And that is not true in real life. Of course, straight lines are not true either. Last thing I'll say as we end is, of course, both these variables could be continuous, X and W. That is harder to visualize, but the idea remains the same, that if you leave off the interaction, then the slope of one variable, the coefficient for one variable, has to be the same regardless of the value of the other.